Welcome everybody to exercise 2 on page 106 of the workbook. And here we're going to talk about a problem that deals with Rapid City, South Dakota, and that's the town that I went to college in. If you ever get a chance to visit Rapid City, I'd recommend it. It's the gateway to the Black Hills. There's some great scenery, but if you're going to go, I would go in the summer because those winter temperatures can be a little bit ugly. So speaking of temperatures, that's kind of what this problem is about that we're looking at. And let's read the information that they're giving us. So the rate of temperature change in Rapid City is given by R of t equals 15 over t minus 6. Okay, and they're giving us that information over a 6-hour period. And t is representing the number of hours after 12 noon. So noon is kind of our starting point. Okay, they've given us the formula to the right. We already noticed that. And the first question is asking us whether the temperature is increasing or decreasing at 2 p.m. Okay, so the first question we might ask ourselves is, what are they really asking for us in part A? Notice that it's a rate of change that they want. Okay, so rate of change of temperature, what would the units of that be? Well, if you think about it, a rate of change would have to be measured in degrees Fahrenheit per hour in the units of this problem. And you might notice that the function that they gave us over here has those units. This represented a rate of change in degrees Fahrenheit per hour. So to answer the question in part A, we should be able to use our function R of t directly. The only question is, what's the value of t at 2 p.m.? Well, since t equals 0 represented noon, that means 2 p.m. must be t equals 2. So all we have to do really here is to plug in 2 to our function and see what we get out. Okay, and if we do the calculation there, 15 over 2 minus 6, that's 7.5 minus 6, which is going to be 1.5 degrees Fahrenheit per hour. Okay, and so if we wanted to just put into words what we calculated, that just means that that's the rate of temperature increase at 2 p.m., so the temperature is increasing. Okay, so we have answered part A for this question. Okay, and moving on to part B, now they're asking a different question. Does it warm up or cool down in Rapid City between 1 and 6 p.m., and by how much? Okay, so let's ask ourselves the same kind of question that we did at the beginning of part A. What are they really asking us for here? So warming up or cooling down, now what we're talking about is a temperature change. So our unit should be in degrees Fahrenheit. Okay, so the question is, how do we take the function that they gave us, which is a rate of change in degrees Fahrenheit per hour, and turn it into information about how the temperature is changing? Well, here it's helpful to think back to the beginning of this section. We talked through a theorem that was called the total change principle. Let me see, was that what we called it? I guess it was the total change theorem is what we called it. And that said that to get the total change in a function, we need to integrate the rate of change. Okay, so we can answer this question by just integrating our derivative. Or actually, I really shouldn't say integrating our derivative. Integrating the function we were given, the function is a rate of change, so it's kind of like a derivative. Okay, so we're going to integrate from 1 to 6 r of t, and that should give us a result because the integral of that rate of change should give us the total change, which is what we're being asked for. Okay, well, let's see if we can do that. So we want to integrate from 1 to 6, and our function is 15 over t minus 6. We need an antiderivative for that function, and to help us do that, we might rewrite that as just bringing that t into the numerator and writing it as 15t to the negative 1. And now we need an antiderivative for that. Okay, well, you might look at this t to the minus 1 and think we're going to use the power rule, but if you look back at the table of common antiderivatives, that power of negative 1, that was that one power where the power rule doesn't work for us, kind of an exception. So what is an antiderivative for t to the negative 1? That's the natural log function. So we're going to use that formula for the antiderivative that says antiderivative of t to the negative 1 is ln of the absolute value of t. And then we come to the minus 6, and an antiderivative for that would just be negative 6t. Okay, we're going to evaluate that between 6 and 1 and see what we get here. So if we substitute in the upper limit, we're going to get 15 ln of 6 minus 6 times 6 is 36. There's our upper limit. Then if we plug in 1, we're going to get 15 ln of 1 minus 6 times 1 is 6. And you might remember from algebra that the natural log of 1 is 0. If you don't remember that, that's okay. You could type that into your calculator and it will tell you that that's 0. So what we're left with here is 15 ln of 6 minus 36 minus a negative 6 is a plus 6. Okay, from there, this is a job for your calculator, and what's going to come out is about negative 3.12. Remember the units here are degrees Fahrenheit. We integrated the rate of change in degrees Fahrenheit per hour and got the total change in degrees Fahrenheit. Okay, so what's the answer to our question then? Well, we got a negative temperature change, so that means that we cooled down by about 3.12 degrees Fahrenheit. Okay, and that would be the answer to our question. Okay, between t equals 1 and 6, which would be between 1 and 6 p.m. Okay, and I think we have finished this problem.